Welcome to this deep dive into the Idle sample world. Today we're going to be breaking down exactly how this game works under the hood. We'll take a look at the core gameplay loop, summoning characters, auto-battling, and earning offline rewards, and give you a complete roadmap of the technical milestones that we're going to cover today, from map building all the way to UI customization. So before we dive into the tutorial portion of this video, let's first press play and take a look at what we're going to be building. So notice that we start with 10 coins. This is because we have offline rewards. Normally we start with a lot less, but we can see enemies spawning in. We can summon in characters using the misos that we earned. We can reposition characters. We can swap characters. We can move them around to strategize where to place our characters to best fight off the impending hordes. We also have a lose condition. And that will be when our wave count reaches the maximum and we have not defeated enemies. So we have a certain amount of time left. If we do not defeat those enemies in that time, then we will lose. So we got 3 seconds left. And we can see that we have the result. We have our highest achieved wave as 1 and our current achieved wave is 1. And we have a high score achievement system here as well. So that is the big picture of what we're going to be building, an engaging endless idle loop. Now that you have an idea of what the final product will look like, it's time to lay the groundwork. So in our next section, placing the map, we'll jump into the editor to set up our play area and explore the vital differences between tile maps and rectile maps. Every great game needs a solid foundation, so in this section, we're going to cover how to switch our map format from a traditional side-scrolling tile map to a top-down rectile map. We'll also take a look at how to use tile sets to design our character slots and monster paths, and show you how to hide the default player avatar while setting up our background music. So this idle game that you see here is of course built on a map, but the map that you start with when you first open MapleStory Worlds isn't the map style that you see here. To demonstrate this, let's open up our map list. And this window can be accessed with Control Alt and 1, or by going into the window and going into map list here. But here's our current map, and just for demonstration purposes, let's create a new map. And that creates our new map, map 01, and let's click load to load this map in. And immediately you're gonna see that the view is slightly different. The background has changed. And when we enter into our tile mode here, we can see that our tile mode is in the maple tile style. So when we draw our tiles in, let's say here, we can see that we have our maple tile style. And this is the default tile editor that you'll get when you first open up a new scene or you create a new project. So to switch to our rect tile mode, we're going to hold this tile editor button down and we're going to switch to rect tile mode. It's gonna caution us that all our existing tiles will be erased, which is fine, that's what we want. And now we have switched to rectile mode. So to switch between the different scenes that we've created, or the different maps that we've created, we have map 01 and our original in-game. We're just gonna double click, and it's gonna say, if you're in co-production, it's gonna ask to check in any changes. We're gonna review them, we're gonna check in our changes, and then we're gonna double click the in-game again, and we can see that we have switched to our map. Let's go back to map 01 by double clicking. Of course, alternatively, we can do Control Alt and 1 to open up our map editor, and we can load our map in this way. So from here, notice that we have our tile set window here, and think of this kind of like a water palette. If you have ever done any kind of watercolor painting before, imagine kind of a painting palette with different types of colors on it. We can select different palettes and different tiles, and we can draw them onto our grid here. To create a tile set, this is already pre-created for us in this sample project, but to create a new one, we can just click this plus button here. Let's first delete by right-clicking and dragging and delete all of our tiles. Let's create a new one, and we can create a tile set from a template, or we can create an empty tile set. Let's create one, let's say BNB, and let's say my new tile set, and we can see that we have a different preset here. So now we have a different set of quote-unquote watercolors to choose from our palette. So we can choose this ground texture here, and we can draw this onto our grid, and we can draw other things onto our grid. We can start building out our world and our map this way. So to kind of replicate the original grid layout that we had, so again, let's save and check in our changes, and let's hop back into our in-game. And let's kind of replicate what we see here. So to do that, we can switch back to our map 01. And let's start drawing out our grid here. So we have an 8 slot grid. So we have 1, 2, 3, 4, 5, 6, 7, 8. So there's our grid for our heroes. Around that, we have the path that our enemies will walk on. So let's build, let's say, kind of a road here. So let's draw this here. Let's do kind of a vertical one down here. Let's do another horizontal one over here, and then maybe a couple more vertical ones here. And there we have our road. I'm not the best kind of artist when it comes to this stuff, but there we have it. Okay, and then on the outside, let's create, let's say, some, boxes to block out our outer area here. So we will have our monsters running around this circle, and we have our heroes that can be placed in the center here. So this is just an example of rectile placement and how we might build our map out. So I encourage you to build your own maps, experiment with our layering system. At the moment, we're just using one layer, but we could theoretically have multiple layers. So for example, I can create another layer here, and down here I can just demonstrate this. So we can have our floor on layer 1, and maybe on layer 2 we can have some trees on top of it like that. So we can kind of have layering textures on top of each other. If we had this tree by itself, it would kind of look strange. So we can have a tree on top of our floor background here. So we can have different ways to build out our maps. We can create little buildings in here. It's a lot of kind of cute ways to decorate. All that said, I encourage you to build your own map for this idle world. Okay, so we've got a couple more setup steps here. If we press play, notice that we don't actually have the avatar visible in our scene anywhere. But if we open up our map, we can see that we do actually have our player entity in our map right here. So the reason for that is our character is just kind of hiding in our scene. It's present, but just not visible. If we look into our avatar renderer component, we can see that it has been disabled. So our character actually is there. It's just we've disabled the avatar renderer component so that you can actually see the character in our game. So let's actually do that. In our default player, if we collapse all of our components, just so it's a little bit easier to see all of the components associated, we have the avatar renderer component unchecked. The enabled property of our avatar renderer component has been unchecked. We also, in our kinematic body component, we can see that we have our kinematic body component disabled as well. Let's also make sure that our enable shadow is unchecked so that the shadow is not visible either. Because it's been disabled, this won't be relevant, but just for good measure, we're going to disable our kinematic body component as well as the enable shadow. And then let's also hop down into our name tag component and make sure that this is also disabled as well. So with that, we have completely hidden our player, and we've also disabled our player from being able to control our avatar completely in our world. So our avatar will no longer be able to move or be seen in our world, and our game will entirely work around our spawning system and manipulating the heroes in our grid. Next up, notice that in our in-game root map entity, we have our BGM player component that will play the BGM in our world when we press play. So if we double click to open this up, we have our onBeginPlay method, which is going to start as soon as our entity is activated or the world begins. You can see our play BGM method being called here, and that will play the corresponding BGM in our property. So we have a property of a type string that will hold the BGM ID, and we can see that in our property inspector, we have the BGM ID, and we've set a certain audio for our world. But we can swap this out easily. We can go into our AI Lab tab, and we can go into Research Search. And from here, we can filter by, let's say, BGM. And we can play a couple of these and just kind of see what they sound like. Sounds kind of ominous. Let's go with that. So we can copy this BGM and we can paste that in here. And in our scene, we can press play. And we have swapped out the BGM in our world. And there we have it. Our map is fully laid out, the default avatar is hidden, and our background music is playing perfectly. but as of right now, our world feels a little bit empty. So coming up in the next section, creating the character will breathe life into our game by building our hero entities, setting up collision groups, and writing the underlying data that defines their stats and gacha drop rates. Okay, let's get into creating the character. In this section, we're going to build the heroes of our idle game. We'll cover setting up visual components, adjusting the collision trigger areas, and enabling drag and drop mechanics. Finally, we'll dive into the data side, creating datasets and struct types to manage character stats, and writing the logic to handle random gacha summons and character slots. Okay, so let's start by creating a new entity in our map. Let's name this character warrior. And to this entity, we're going to add two components. We're going to add the avatar render component, which will show our avatar and be able to render out our avatar. We're also going to add in the costume manager component, which will complete our avatar. Now, we are currently rendering my avatar, but since this avatar will be used as our heroes, they need to have custom equipment and accessories. So we're going to have use custom equip on toggled on, and this will make sure that this costume manager component is only rendering based on the properties that are set here. Custom body, custom cap, custom cape. So only the fields that are set here will be actually rendered on our character. To this, we're also going to add in the state component to track the various animation states. And finally, let's add in a trigger component to detect the attack hitboxes. So for the trigger component, let's change this to a circle type. And we're going to modify this trigger radius to be a little bit bigger. So let's increase it up. And this will be the range that our hero will detect the enemies and start attacking. Next up, let's open up our collision group and notice that we have two new collision groups. We have the character attack range and we have the monster collision groups. Both of these are necessary. We'll go into the matrix and also double check that only the character attack range and the monster, the part where they intersect, is where we check. So this will ensure that this trigger component is only detecting what's necessary and ignoring everything else so that we don't perform any unnecessary calculations for any collisions. Okay, next let's add in our unit controller, which is a pre-existing component that exists in our project here. And if you don't have this and you want to build this from scratch, you want to right-click in your workspace, go into Create Scripts, and click Create Component to create this component, and then attach this to our hero entity. So let's search for Unit Controller and attach this to our entity. So this completes our hero, but we also, if you remember, have the ability to drag our hero into different slots. So we're going to actually create another entity as a child here that will handle the dragging. So this will act as our dragging entity, and this should also be able to render the character avatar. So let's attach the avatar render component as well as the costume manager component. And let's also make sure that the custom equip on is toggled on. Let's zero out our position so that the local position is right on our character. And because we're going to be detecting drags, let's attach the touch receive component, and it will detect any touches that intersect with this entity. And we also have a drag component, and we're going to get into this as well, but this will be a component that handles the drag logic. So this is a custom component that we've created to handle what happens when we detect a drag and what happens when we let go. Let's rename this entity to be drag entity, and let's disable this. So we'll set the visible to false so that only the visibility is toggled off, but everything else, like the touch receive component and all of this other stuff, all of the logic behind the drag, is still interactable. Now that we have that, we can right click and we can click create model from entity, and models will essentially allow us to create a kind of blueprint of this entity. So we're gonna have a lot of warriors here depending on how many slots you have. At the moment we only have 8. But to recreate this character warrior every single time is kind of a hassle. So by creating this model, now we have a blueprint that has saved all of the settings that we've just set up for this entity. And if we right click and we click on place to hierarchy, we can see that we have the exact copy of our entity being dragged onto here. Let's delete that. Let's also delete this. Because we already have our character over here, we have 3 different types. We have one for the archer, we have one for the mage, and we have one for the warrior. Notice on each of these, we have our costume manager component, and each of these have a custom setup for the body equip, the cap equip, and we've kind of dressed each of these avatars up in the corresponding class archetype. So for the archer, we've dressed this character up. For the mage, we've dressed this character up accordingly. And finally for the warrior, we've dressed this character up accordingly as well. You can create more, but for now, in this sample, we only have 3. Now that we have our models for the archer, the mage, and the warrior, we have to also be able to define various stats that differentiate the archer, the mage, and the warrior from each other. What is the attack rate? What is the spawn chance? What is the attack speed? What is attack damage? Etc, etc. This data is stored in what's called a data set, and this is different from our data storage, which is persistent data. Data set is normally used for configurable tables for modifiable data, and data that kind of define the baseline stats or information for our game. So a couple of these that you might see is things like the monster data, the skill data, wave information for how many monsters spawn, the character data for our character. So let's double click on our character data and take a look at some of the tables here. So first up, we have our character ID, and this is going to be our unique identifier for each of our characters. So character underscore warrior, character archer, and character mage. Then we have the grade, which is going to be our rarity. So character warrior is the lowest tier, the archer is next up, and the mage is the most rare. For our base attack value, we can see that the warrior has 15, archer has 20, and mage has 30. The attack animation is going to be what animation plays when the character performs an attack. So the list of animations associated with our avatar can be found in our documentation. If you search animation, you can see that we have our controlling animations page here, and we can see a list of all the action names here. So you can choose from each of these, and we can define them in this table here. So we have swing T1 for our character warrior, we have shoot, and swing 03 for our character mage. Then we have the effects that will spawn associated with the attack animation, and we have unique attack effects for when they hit our enemy. We also have the attack range, which will define the range relative to the trigger area that we have set up here. So this is going to be that circle radius that we've set up. And then our attack cooltime will be the attack rate for our characters. Then we have the model ID. So this will be referencing the models that we've created earlier. So we have the archer, mage, and warrior models. And if we right click and click copy entry ID, this will be what is actually being referenced in this table entry here. Then we have skill data, and this is going to be referencing another table that we have. So if you open up our skill data, we can see skill underscore heavy slash, rapid arrow, and thunder. We're going to get into this table and its contents and what it does in just a moment. But for now, let's focus in on our skill data table here. This is just going to let us know what skill is going to be performed when the skill is activated. So for our warrior, it is going to perform the heavy slash, archer is going to do the rapid arrow, and then mage is going to be the skill thunder. Okay, another table that I want to highlight is the gacha rate data, and we can see that we have different grades. So in our character data, we have grades associated with our characters. We have a warrior of grade 1, archer of grade 2, and mage of grade 3. In our gacha rate data, we can see that we have a grade and an associated rate value. So this is going to be the percent chance that our characters will be able to be spawned. So grade 1s have a 65% chance of appearing, grade 2s have a 25%, and grade 3s have a 10%. At the moment, this does add up to 100, but depending on the number of grades that you plan on, these values might differ. So for each of our data sets here, we also have a corresponding struct type. So we can see that our character data has a struct type of character data. And this essentially is the code version of our data set. So we're going to have a different kind of data manager logic that will manage how the data is loaded into our structure objects. And each of these data columns will be loaded into their corresponding properties. So we have one for character data, and we have a column that exactly matches the column of our data here. Character ID, grade, basic attack value, character ID, grade, basic attack value, and so on. Same thing for our gotcha rate data. We have our grade and our rate value. And we can see that in our gotcha rate data, we have the grade and rate value listed here. To begin, let's take a look into our character gotcha logic. So the character gotcha logic is going to be handling the logic for spawning our characters into our grid. So let's go down these properties here and take a look at what they do. So first we have the first three tables. We have our character data, gotcha rate data, and skill data tables. Each of these is going to be corresponding to the data tables that we looked at, the character data table, gotcha rate data, and skill data tables, and they're going to be loading them and creating our struct types. So remember, we also took a look at the struct types down here. So in our code, we're going to be loading that into the corresponding struct types and then adding them to this table. So we're going to have our data table loaded with all of the data that's associated with our data sets here. So how is that working? So we have our init character data. If we open this up, we can see that we are grabbing the data table character data. So we're going to grab this character data from our get table of the data service. Once we have that and it is actually valid, if it's not, we're going to return. We're going to grab the total row count and we're going to loop through each of those rows. For each row, we're going to grab each column, character ID, grade, basic attack value, all of those, and we're going to load them into the character data struct type. So we've created an instance of our character data struct type here, and that creates an object with each of these properties. And for each of those properties, we're going to load in the values. Once we have all of those values loaded in, then we're going to grab our character data table and we're going to index it by the grade and add our new character data to that character data table. So essentially what this has done is it's created a multi-level table. At the base root of our data table, we have a table of all of our grades. And then from each of those grades, we're adding our character data to those grades. So we have a table of tables. Each of those table entries is a table of grades. And for each of those grade tables, we have added our character data in. We're going to do something very similar for our gotcha rate data. So if we open this up, we can see that we have a very similar pattern. We're going to grab our gotcha rate data here, and we're going to verify that it exists. Then we're going to loop through all of the rows and we're going to grab the grade and rate value and add them to our gotcha rate data struct instance. Then we're going to insert into our gotcha rate data the rate data entry here. So this is just going to be a straight one-dimensional rate data. This is just going to be a simple one-dimensional data table that just contains all of our rate data, as opposed to our two-dimensional character rate data that has each of our grades, as opposed to our two-dimensional character data table that has a table of grades, and each of those grade tables has a list of all the character data. Now our final initializer is going to be the init character slot group. And if you open this up, we can see that we have our initializer, and we're going to initialize and grab the character slot pose group. So this is going to grab our character slot group component, and this is going to manage all of the slots that we have in our map. And we can notice that we have a character slot group component attached to this, and that is what we're looking for here. So we're going to grab this entity, and then we're going to find the character slot group component. Once we have all of that initialized, we have all of our data set up that we need to start blocking in our logic in earnest. So our getRandomGrade method is going to add up all of the rate values that we've grabbed from our gotcha rate data. We've just loaded that in, and we're gonna grab all of the rate values. So this rate value, remember, is a struct type. So it's grabbing this rate value, which of course has been loaded in based on this table column here. So going back to our character gotcha logic, we can see that we are adding all of those rate values together, getting the total value. Then we're going to randomize a random number from 1 to that total value, and we're going to return the corresponding grade. So this is essentially just going to pop out a random grade based on that chance. So it's going to kind of run the gotcha and return a random grade based on these percentage values that we've set here. Now that we have the random grade, we need to be able to grab the character from that grade value. So that's why we have the getRandomCharacter by grade value here. We're going to pass in the grade value. We're going to grab the list. So remember, this is a 2D table. We're going to index it by the grade value, which is going to return a table of all the characters of that grade value. Then we're going to randomize from 1 to the total length of our table. We're going to return a random character from that list. So our random grade returns a random grade. Our getRandomCharacter returns a random character based on that grade. Now we have an alternate method here, get random character data, that does not require a grade value to be already passed in. We will randomize the character data, and we're going to completely call this function again so that we grab a random grade, pass that into the get random character grade value, and return that random character. So one method depends on a grade value to already be known. The other one doesn't care about the random grade value and is going to generate a random grade for you and return a character based on that randomly generated grade value. Once we have the character data, we're going to need to actually spawn them in. So that's where our request spawn character comes in. So our request spawn character is going to first check if we have enough summon tokens. So this is going to be the cost for summoning our character into our grid. So once we click on spawn, we're going to grab a random empty slot and check if there is an empty slot. So if there is an empty slot, then we're going to spawn our character to that empty slot, and we're going to update our summon tokens so that we subtract 1 from our tokens. Otherwise, we're going to show a message saying that we have no more spawn. If we don't have enough tokens, we're going to notify the user that you have insufficient tokens. Okay, moving on, we have already set up our summon logic for our character gacha. We know how to grab a random character based on that grade. We know how to load in that data. Now we need to be able to understand how the slots actually work. So remember that we have referenced the character slot group controller to return an empty slot, but how are we actually determining that? So first up is our entity setup. So if we go back into our scene, we have our character slot pose group, which is going to be a list of all the positions of our slots. Each of these slots has a sprite render component with this cool, spawn animation here. And we also have a character slot component attached to each of these. In our main kind of parent, we have our character slot pose group. We have the character group component that we had referenced in our character gacha logic. So our character slot group component is going to be managing each of these slots, and each of these slots has a character slot component associated with it. Down at the bottom, we have a character group. The character group is going to be what actually holds all of our character entities. The character slot is going to be essentially just marking the position of spawn, but the parent is going to be our character group. With that said, let's open up our slot component and take a look at this. So this slot component is going to be associated with the position values here, position 1 through 8. And our properties hopefully is fairly self-explanatory. We have first our current character entity. So this is going to be the entity that is actually assigned to this slot. And we also have an index for our slot number, whether it's 1 all the way to 8. Next, we have our check can spawn character. We're going to double check to see if we already have a character assigned to this slot. If we do, then we're going to return true. Otherwise, we're going to return false. So pretty simple logic there. And then we have two initializer methods. The first one is going to actually assign the character entity to this slot. So we're going to pass in the character entity to assign. We're going to assign that to the character entity, in which case this will kind of change this flag here to true. And we also have the init slot number, which will assign the slot number to our slot number property. We also finally have a get slot number that returns this slot number. So that is our character slot. Next up, we have our slot group component, which is going to actually manage all of our slots. And again, remembering that this is what actually is the core logic that we call for our character gacha logic. So first up, we have our properties. We have our character slot list, which is going to hold all of these property entities that we have here. Then we have our character group, which is going to be the entity for spawning in our character models. So this is going to be the model that actually holds all of our characters. And then finally, we have a property for is dragging. So this is going to be a flag to determine whether we're currently dragging the character or not. Let's start with our onBeginPlay method here, and we have two initializer methods here. So we have init character slot list, and this method is going to populate our character slot list with each of the slot entities here. So we're going to loop through all of our current entities. So this is going to be the character slot group component because that is our parent. We're going to loop through each of our children and we're going to grab the character slot by name. So we're going to concatenate our character slot position with the index, and that will grab our character slot child. And we're going to validate if it's a valid entity. If it is, then we're going to grab the character slot component. We're going to initialize the slot number to our current index. Next up, we have the init character group. And this is a lot simpler. We are simply just going to find our character group entity and assign that to our character group property. Next up, we have our return empty slot number. And this is what is actually called by our character gotcha logic. If we go back, we can see that we are looping through each of our slots. Remember, we have initialized all of our slot components and searched for all of them. So we are calling the can check spawn character. If we go back, we can see that the can check spawn character simply checks if we have an entity assigned. If it does, we're going to return true. Otherwise, we're going to return false. So if we can spawn a character, then we're going to return the index of the slot. Otherwise, we're going to return 0. Next, we have our spawn character, and this is going to be actually spawning the character to our slot. So we have a slot number that we're passing in, and we have our character data. So we have our spawn character here. We're going to call spawn service spawn by model ID. So our character data, if you remember, holds our model ID. So going back to our character data, we have our model ID. This is referenced and loaded from our character data model ID field here. So going back to our slot group component, we have our model ID, character ID. We're going to spawn this at the local 0 position of our character group. So remember, we have our character group parent entity here that we're going to spawn it into, and we're going to spawn it at a local 0 position. Then we're going to set the spawn's position to the slot's world position, and we're going to init our character data with the character data that we passed in. Finally, we're going to call init character entity and pass in our spawn character so that our slot knows that we have a character associated with the slot. Next up, we have a switch slot character method here. So first, we're going to check if the slot has a character entity. If it does not, then we don't actually need to swap. We're just going to simply set the slot of that target slot. So we're going to call our unit controller change slot, and we're going to initialize our target slot's character entity, and then we're going to initialize our previous slot to nil. If there is a character already associated, then we're going to swap the two characters together. Our existing entity is going to swap to the previous slot's entity, and then our target entity is going to change to our target slot's entity. Then we're going to initialize both of those slots with the corresponding entities. Our clear character list is going to clear all of our characters from our slots, and we're going to initialize all of our slots to nil. So this will be relevant when we start a new game, for example, where we want to destroy all of our characters and start again from a clean slate. Finally, we have the dragging logic. So in order to call switch slot character, we need to actually have the drag logic. So for our dragging, let's go to our drag component and let's double click this. So in our drag component, we have a few properties to take a look at. First, we have our index, which is going to hold our touch index. Next, we have our handlers for our current dragging and our release handlers. We're going to cache both of these so that we prevent duplicate event handlings. Then we have the slot entity, which is our current slot entity, and we have the parent entity, which is going to cache the current parent. So if we remember, we have our character and we have a drag entity. This drag entity has this drag component attached to it. So we're dragging this entity, but the actual entity that we want to switch is going to be this parent entity. So in our drag component here, we're going to cache this parent entity, and we're going to also have a cache of our character slot group. So the core of our logic is going to be listening in on this handle touch event. So this is a base event that is going to be fired by our touch receive component. And we're going to grab this event, we're going to grab the touch ID of this event, and we're going to call add handler. In our add handler, we're going to first double check if we already have a handler. If the handler is already running, then we don't want to have a second touch to be processed. We're just going to process the first touch, and that's it. We don't want any overlapping touches. Then we're going to double check to see if we have our character slot assigned, and we're going to set the dragging flag to true. So we're going to grab our cached character slot group, and we're going to check if this dragging flag is true. If it is, then we're going to return. Otherwise, we're going to set the dragging property to true. We're also going to set the visibility to true because our default state is false. So we're going to set our visibility to true. Then we're going to insert our current touch ID to the index. So this is going to be a table of all the touch IDs. And then we're going to set up our handlers for our touch event and our touch release event. So our touch event is going to be bound to our move method, and our release event is going to be bound to our onRelease method. So first up, we have our move method, and our move method is just going to grab the screen hold event's touch ID and the touch point, and we're going to transform our touch point, which is in screen space. So we're going to change it from screen space to world space by calling our UI logic screen to world position, and that will give us the world position from our screen position, and we're going to change that to a vector 3. So this will give us a vector 2, world position is vector 3, so we're going to convert that to a vector 3 and assign that here. Our onRelease is going to first disconnect the event for our handlers for our touch event for both the hold and the release events. And then we're going to search for the closest slot, and we're going to switch that slot with our target entity. So we're going to grab the target slot number and the before slot number and pass that into our switch slot character. And we took a look at that in our slot group components before. So we already know what that does. Then we're going to reset the world position to our parent entity's world position, and we're going to set the visibility to false. And that's it. Great job. We now have fully functional character models, a structured data system for their stats, and the logic in place to summon and place them on the map. But our heroes need something to fight. So up next, we're gonna cover creating the monster, where we'll construct our enemies, map out their portal paths using tween lines, and give them health bars and damage controllers. Welcome to creating the monster. It's time to bring some bad guys into this world. So in this section, we're gonna set up some monster visuals and animations, and we'll also use what's called the tween line component to make them patrol around our map automatically. We'll also optimize their collision settings and create the datasets and controllers needed to manage their health and death states. Okay, so let's begin by adding a new sprite and creating our mushroom character. So let's create a new empty sprite. That's going to come packaged with our transform component and our sprite render component. So for our sprite RUID, let's add a mushroom character to this. So we can search through our research search tab, and we can find this under our AI lab tab. And this is our research search window. And this is our way of allowing you to easily search for assets that you need. So we can filter by types. For the types, we'll select resource pack, and this will give us a pack of packaged animations. And let's set the category to monster. Our search keyword will be mushroom. So if we search for mushroom, here is that standard mushroom that we all know and love. And we're going to make a note of the move animation. So let's copy this animation and let's paste this into our sprite RUID field. So there is our move animation playing, and let's also make a note of our die animation here. So we're gonna need this later, but for now, let's just hit our favorites and allow it to just sit in our favorites for a little bit. And we're gonna come back and we're gonna copy this die animation for later on. But for now, let's leave this as is and move on, creating our mushroom sprite here. So let's also add our tween line component. We mentioned that we will be utilizing this to create our pathing for our character. So we're going to set our tween type to linear. We have a lot of different patterns. We're just going to have a linear pattern. Our stop type will be one way, so that once it makes one round trip, that's it. We're going to set our destination coordinates to absolute, so that it's not relative positioning, it is absolute positioning. And for this, let's create an empty sprite. And let's set this maybe around here. So let's say negative 2.5 and 2.5, 2.4. That seems reasonable. So let's copy this position, negative 2.5, 2.4, and paste that into our positions. So we're gonna create 5 positions here. We're gonna set this starting position as our first position. Then down in this corner will be our second position. We got our third position here, right there. We got our fourth position right there. And then we got our fifth position right back at the start. So this will complete our loop. So we are going to need 5 positions here. So let's utilize this as our kind of guide and start copying down the relevant positions. I've just finished setting mine up. So I've got all 5 of my positions here. We've got our starting position, and then we've got the 4 corners, and then we've got our starting position again. So it's gonna go around and stop. For our interpolation type, we're gonna set none. For our auto start and auto destroy, we're gonna keep this unchecked because we are going to handle the destruction. For the sync type, we're gonna make sure that this is set to client only. next to track collisions, let's add a trigger component. Let's keep our collider typed to box. We'll double check to make sure that the trigger range is in the appropriate range. It is, so we're just gonna keep this as is. And for our collision group, let's set this to a monster. So we have added our own custom collision group here, and we've created another one. If you want to create more, you can click on this add collision group here. But we've created two. We've got character attack range and we've got monster. Now let's hop into our matrix here, and let's double check to make sure that our collision matrix is set up such that our character attack range collides with monster, and everything else that's not necessary will be unchecked. So we're going to double check to make sure that we are optimizing our collision matrix. For further optimization, we're also going to make sure that is passive is checked on. If we check this, it's going to make sure that it won't perform any collisions against itself. So the monster will not collide against other monsters. This is passive is going to make sure that other components, other trigger components, are calculating collisions against this entity, but this entity isn't going to detect any collisions against other things. So we're just going to make sure that this is one way coming into this monster, but no collision detections are going to happen from our monster itself. So that's what the is passive is going to do. We're just going to make sure that we're not calculating any collisions. We're just going to make sure that other collisions will be able to check against our collision area here. Okay, next up, when our monster takes damage, we're going to want to make sure that we display some damage numbers. So let's add in the damage skin component. And finally, we want to track the health of this monster visually. So let's add another sprite as a child. And this will be our HP bar. So let's rename this to HP bar. So for the sprite for our HP bar, we can search under the resource search window again. And this time, let's search for a health bar. And if we take a look around here, we can take a look at some of the sprites. If we select one, maybe this one here, and then we can copy the RUID again, and we can paste that right into our health bar sprite RUID field right there. One note I will make about this is that depending on your pivot, you can kind of see the pivot point where there's a little overlapping circle right there. There's the position or scaling widget here, but underneath that you can see a kind of circle. That is where the pivot of our sprite is. So depending on the sprite that we select, so let's say for example we selected this one, copy the RUID, we paste it into the sprite RUID field. We can see that depending on the sprite, the pivot is in a different position. So in our code, when we manipulate our health bar, we are adjusting the scale. So the scaling will go up and down depending on where that pivot point is. So ideally, the pivot point should be either on the very left side or it should be in the center. So please do keep in mind as you search for sprites, keep an eye on that pivot point and see where that pivot point lies as you select your health bar. So let's check this one here. And if we copy and paste this RUID field into here, we can see that this pivot point is right in the center. It's a little bit above, but it is relatively center, so that when we scale up and down, we can see that it scales into the center here. An additional note is that our HP bar, if we go into our existing model here, we can see that we have our monster controller. If we go into edit script, we can see that we have our get damage method. We're going to get into this, but we can see that our HP bar is scaling by the monster data start HP, and that will give us a fraction out of 1 and give us the fraction to multiply against the size of our HP bar. So in our orange mushroom model here, we can see that we have the scale set to 10. If we set this to 1, we can see that it's very, very tiny. So we're going to set this in code to 20. So that when we scale it up and down, we're creating a fraction out of 20 here and scaling it down depending on the remaining HP. So keep that in mind. So when we select our HP bar here, let's say we want this to be the scale of our HP bar, then we're just going to be scaling out of 1. Or if we want this to be our HP bar, we're going to keep a note of the proper scale or the full scale that we like, and then make sure that we adjust this portion here so that we multiply the scalar by the actual final scale. Okay, now that we got that HP bar out of the way, let's go back to our parent in our mushroom. Let's make sure to name this something that makes sense. Let's name this, for example, monster underscore orange mushroom. And let's also finally add our monster controller. So this monster controller, we're going to get into the script for this, but this will be the component that actually controls the monster's behavior. We just saw that one of those behaviors is adjusting the monster's HP bar and adjusting the damage value, but let's double check to make sure that we have added this component. Or if you're building it from scratch, make sure to create a new component called monster controller. You can right click and you go into scripts and you can use create component to create your own component if you'd like. And then we can right click and we can click create model from entity. This will create this model here. Notice that we have two different models here. We have one for stone golem and we have one for orange mushroom. This allows us to create kind of a blueprint of our mushroom so that we don't have to recreate this from scratch every single time. We can just keep this blueprint and just work off of this blueprint. So if we click create model from entity, that will create this model of our mushroom that we have just created. And we can add that to the monster list. So feel free to create your own monsters, but for now, let's delete this model and let's also delete this mushroom that we've created. Let's hop into our monster controller script here. So that will go in the monster component. We can see our monster controller script. Let's double click to open this up and let's take a look. So before we actually look at the monster controller here, let's pause and actually take a look at the data for our monster. The information for our monster will be contained within our monster data table. So notice like we have in our models, we have two, we have orange mushroom and we have stone golem. For each of these monsters, we have different values. So we have the 1 cycle move time, which is going to be the movement speed. We have the start HP, which is going to be the starting HP of this monster. And we also have the model ID to spawn into the world. So this will be in reference to this entry ID right here. We also have a unique identifier for our monsters. So that is the data for our monster. Based on this data, we have a structure. So if we right click and we go into our scripts, we can see that we have a struct type here. If you double click to open up the monster data struct type, we can see that we have properties corresponding to our monster data column. So we have monster ID, 1 cycle move time, etc., matching properties in our monster data. So with that, in our monster controller, we have a field for our monster data. So this will be a property containing this struct. This data will have been loaded externally and passed in by init data. So externally, we're going to have already loaded this monster information, and we're going to be passed in the data for this monster. So when we get this monster data information, we're going to set the monster data to the monster data, and we're going to set up the relevant initializers based on this data here. So for example, the tween line component's duration is going to be the 1 cycle move time. This is going to manipulate the final move speed of our monster. We have our current HP set to the monster data starting HP. We have our isAlive property, which is just going to be a Boolean flag. We have our enable property, which is going to set the activation status of this component. And then we're going to make sure that we stop our tween line component if it's already been running. We're going to set the world position to the starting position, and we're going to set the scale of our HP bar to the starting HP. So we have our current HP divided by start HP. At this point, this would be a fraction of 1 multiplied by the width. So keep in mind that width that we talked about when we were looking at the HP bar. And then we're going to set the spawn controller to the monster spawn controller. So this will be the controller that actually spawns this monster in and passed in this monster data. In our monster controller, we also have the onBeginPlay, where we are going to first double check that we have the tween line component, and we're going to set up our references. So we're going to find the tween line component that is attached to our entity. If the entity exists, then we're going to assign our tween line component property to the entity that we found. We're going to do the same thing for the sprite render component. We're going to cache our sprite render component. We're also going to double check our HP bar, and we're going to set the reference for that. And then we're going to set our isAlive property to true. We have our tweenline component, and we're going to grab the current state of our tweenline component, and we're going to check if it's idle. If the tweenline component is currently not active, or it's not currently running, or if it's just finished its tween, then we're going to restart back from the current position. And this will allow our monster to continue to cycle over and over again, despite our monster being a one-way stop type. This allows this monster to continue to loop. Next up, we have our set enable state. This is going to start and stop the tweenline component, and we're going to do some initialization steps here. And then finally, when we take damage, we're going to grab the attack value and subtract our current HP by that attack value. If it's less than 0, then we're going to defeat this animation. So we have our sprite RUID here being set to the die animation key. And if you remember, I asked you to save that mushroom sprite. So if we go back to our resource search here, we have our favorites. We're going to click here and we're going to grab the die animation. We're going to copy this RUID, and in our model, we're going to make sure that our die animation key is set to this value here. We're also going to copy our move animation and copy this RUID and set that value right in here so that we have a value for our move animation and we also have a value for our die animation. Going back to our monster controller, we're going to set the RUID. Once our HP reaches 0, we're going to set the RUID to the die animation key, set the scale to 0 for our HP bar so that we don't see the HP bar anymore. Then we're going to notify our spawn controller that we have one less monster in our world. Then in our game logic, we're going to update our summon token to reward the player with 1 summon token. Otherwise, if we still have HP remaining, we're just going to set the HP scale to the fraction of our HP multiplied by the width of our HP bar, which is currently hard-coded to 20. But again, make sure to modify this value depending on the scale of your HP bar. Finally, we have our handle sprite animation player end event, and this is going to be called when the animation has completed, and we're going to check if the current animation of our monster sprite renderer is the die animation. If it is, then the die animation has just finished, and we're going to set the entity's enable status to false. This is essentially going to return this object back to the object pool. And again, we're going to get into that later when we talk about object pools. And that's it. We've successfully created moving living monsters complete with health bars and optimization tweaks. Now we have characters and monsters on the same map, but they aren't interacting yet. In our next section, we're going to implement character attacks, where we'll connect the two by giving our character skill data, tracking enemies in range, and finally letting the auto battle begin. Now for the fun part, implementing character attacks. In this section, we'll define our skill data and write our unit controller script. We'll cover how to track monsters entering and leaving our character's attack range, calculate cooldowns, and trigger animations and damage so our heroes can finally start fighting automatically. So let's start again with our data set. Let's go into our skill data and take a look at this data table. We've got our skill ID with the unique identifiers for our skills. We have our skill effect, which is going to be the effect that appears on the enemy when they're hit. We have our character skill effect, which is going to be the effect that appears on the caster. We have the skill attack, which is going to be the damage that is applied. And then we have the skill cooldown, which is going to be the amount of time that it takes for the skill to be recast. As always, for our skill data, we're going to have a corresponding structure. So let's go down into our struct types, and we have our skill data structure for each property that corresponds to the skill data here. So we have our skill ID, skill effect, character skill effect, etc., each represented as a property in our skill data table. We're going to load the data from here and organize them into the skill data type, which is going to contain each of these properties. Next up, if you remember, we had our character model that has our unit controller attached to it. Let's double click to open up our unit controller script, and let's take a look. Let's start with the properties for our unit controller. First up, we have our avatar body component. This is going to be important for animating our character. Then we have our enemy table, which is going to be a property for holding the enemies that are within our attack radius. And then we have our basic attack delta and our skill delta. which is going to be our counters for the cooldowns for basic attack as well as our skill attack. Then we have our character data as well as our character skill data, which is going to be caches for the struct types for the relevant data. So we have for our skill data and our character data, which is going to be contained as skill data and character data as struct types. We're going to cache those into these properties here. Then finally, we have our trigger component, which is going to be caching our trigger for detecting the enemies in range. So in onBeginPlay, we're going to be initializing all of our components here. So for the avatar body component, we're going to be searching for the body. For our drag component, we're going to be searching for the drag component. For the trigger component, we're going to be searching for the trigger component. So with our drag component, we're going to also call init drag component sprite. This is going to be setting up the visuals for the drag component. So we have set up our visuals for our character. Our drag component is going to be copying each of the values from the costume manager component. So for the body equip, cape, cap, coat, etc., we're going to copy all of our current costume manager into the drag visuals. Then we have change slot, which is going to be setting the current slot to the target slot that we're changing into. And then we have our onUpdate, which is going to be handling the auto battling system. So we have our skill delta and our basic attack delta, which is going to be incremented by our update delta time. And once we reach the threshold based on our character skill data, and again, retrieving that skill cooltime value, so this will be this column here. Once we exceed in seconds the necessary cooldown for our skill, we're going to perform a skill attack. If it exceeds the necessary delta for our basic attack, then we're going to perform our basic attack. Then actually going into our basic attack. For our basic attack, we're going to be looping through all of the enemies in our enemy table. We're going to double check to make sure that this enemy has a monster controller and it's actually still alive. If it is, then we're going to set the target enemy to the enemy of the current loop iteration, and we're going to break the cycle. If it's not, then we know that either the entity does not have a monster controller or it's not alive, so we're going to remove that from the valid enemy tables list. Then we're going to do a validation check just to make sure that the target entity that we've set actually exists. We're going to reset our basic attack delta so that this is going to reset the timer for our attack. Then we're going to perform the animation for attacking. So we're going to send the event called action state change event to the body component. So this is going to be passing in the attack animation ID, and we're going to be passing in the play rate as well as the play type. So we're going to be playing this one time, and that attack animation ID is coming from our character data. We have the attack animation right here. So we're going to pass that into the avatar body component as an event to change the action state to the corresponding animation. Then we're going to play the corresponding effects for our basic attack. So we're going to play the basic attack effect on the entity and the basic attack hit effect on the target entity. Then we're going to be dealing the damage based on the character data's basic attack value. The skill attack is going to be very similar. We're going to be grabbing the target and an entity in the same way. We're going to reset the skill delta. We're going to set the attack animation ID. So this is going to be the exact same attack animation ID that we sent. We're going to send that to the body component. Then we're just going to play the character skill effect based on the character skill data. So rather than grabbing it from the character data table, we're going to be grabbing this from the skill data table. And then again, we're going to be dealing the damage based on the skill attack value of the character skill data. Hopping down into the trigger enter and leave events. On the enter event, we're going to be checking if this is a valid target, meaning that the collision group is the monster collision group. Then we're going to double check if the table already contains this enemy. If it does not, then we're going to be inserting this enemy into the enemy table. Otherwise, because our enemy table is empty, we're just going to be inserting directly into the enemy table because this is the only one. On the leave event, we're going to be checking again if this is a monster by checking the collision group. Then if our enemy table is greater than equal to 1, then we're going to loop through and check for the enemy table for that trigger body entity that just left. We're going to remove from the enemy table that index. So we're going to be removing that enemy from our list of valid enemies. And just like that, the auto battler mechanics are alive and working. So we've learned how to track targets, manage cooldowns, and apply damage. However, right now we only have the monsters manually placed. To make this a true game, we need endless waves. So coming up in spawning monsters, we'll create the data and logic needed to automatically spawn continuous waves of enemies. Welcome to Spawning Monsters. An idle game needs a continuous flow of enemies, so in this section, we'll define our wave data to dictate what spawns and when. Then we'll build a monster spawn controller and the logic needed to read that data, spawning monsters at regular intervals right in the center of our map. So our wave information is of course contained within our wave dataset. So let's double click to open up and take a look at what is going on in here. So first we have our wave index. So this is going to be the index of the current iteration for the monster to be spawned. So in wave index 1, we have monster orange mushroom and the monster spawn count of 10. So we're going to be utilizing this unique key referencing this monster data. So notice that our monster data shares this same key here, monster orange mushroom. And if you go back into our monster wave data, we can see that we have our first wave index to spawn 10 mushrooms. Wave index 2 will spawn 20 mushrooms. Wave index 3, 30, 4, 10, 5, 20, etc, etc. So we have, as the waves progress, we're going to spawn different numbers of monsters and even different types of monsters throughout our waves. Of course, we also have this data stored through our wave data struct type. So we need a way to hold this information. So we're gonna create this wave data and structure it within this struct type. So we have our property for wave index, spawn monster, and spawn monster count corresponding to each of these columns. So if we take a look at our map, so let's go back into our scene and double click on this monster spawn controller here. We can see that we have this monster spawn controller attached to our entity, and this is going to be the logic for spawning the monsters into our map here. So let's open up this script and take a look at what is going on. Okay, let's start with our properties. First up, we have our monster list. And this is going to be a cache for the monsters that are spawned in our scene. Then we have our wave index to indicate the current wave. We have our standby time, which is going to be the fixed delay between waves. This is not variable, this is just a fixed standby time. We have our spawn position, which is going to be the starting spawn position of our enemies. We have our timer ID, which is going to be tracking the active timer service. We're going to get into what that is in a moment. But when we start a timer using our timer service, it returns an ID for the active timer. So we're going to cache the active timer through this timer ID property. Then we have our entity spawn count, which is going to be keeping track of how many entities to spawn into this wave. We have our maximum spawn count, which is going to be the maximum number of enemies to spawn in the wave. Then we have our current spawn count, which is the number of enemies that have spawned into our map so far. We have our remain monster count, which is going to be the number of monsters currently alive on our map. Then we have our max remain monster count, which is going to be the maximum number of monsters that can be present at any given time in our map. Then we have our isFinish data, which is going to be tracking if we've exhausted all of the monsters to spawn based on our wave data. Finally, we have our pause spawn, which will give us the ability to pause the spawn of our monsters. And that covers all of the properties that will be covered in our monster spawn controller. Let's get into the logic of what is actually happening. So first, in onBeginPlay, we're going to be setting our wave index to 1. So we're going to initialize the wave index to 1. Then we're going to, in UI manage logic, we're going to be updating our monster count to our UI. This is going to be updating our monster UI, and we're going to pass in our remaining monster count as well as our maximum monster count. Then we're going to call initWave to initialize our wave. In our initWave, we're going to be initializing our UI manage logic, and we're going to set up our wave count based on the current wave index, which of course is 1 when we first start. Then we've got our spawn data. We're going to be utilizing our monster spawn logic to get the spawn list. So let's pause for just a moment and hop into our monster spawn logic and cover what is going on there. So let's double click to open up our monster spawn logic. And again, remember that logics are scripts that are globally accessible across all components and all logic files. So components have to be referenced by the entities themselves, but logic files aren't tied to any entity and they're globally accessible. So first, in our properties, we have our monster data and wave data, which is going to be caching both data sets for our monster data as well as our wave data. We're going to be needing both of those to start crafting our data tables for our monster. In onBeginPlay, we're going to be initializing monster data and the wave data. So in our init, we're grabbing the data table, monster data. So this is going to be grabbing this data. We're going to loop through each of the columns in our data table. And for each of them, we're going to be creating a new monster data struct type. And we're going to load in for each row. We're going to get the column for cycle move time, start HP, model ID, all of those. And we're going to load them into this monster data. And we're going to create our monster data. And we're going to populate our monster data with this monster data information. For the init wave data, we're going to do something very similar. We're going to grab the wave data table. So that will be this table. We're going to loop through all of the rows. And for each column, we're going to create our wave data table. And we're going to loop through each of our columns and load those columns into the corresponding properties for wave index, spawn monster count. And then we're going to load that into the wave data table here. So now that we've got both of those data, we're going to have two retrieval methods here. So we have the ability to retrieve the monster by the monster ID, and that's going to be able to check our monster data table for the monster corresponding to the monster ID and return that monster. We also have the get spawn list. So we're going to be passing in the wave index, and based on that wave index, we're going to return the wave data. So hopping back to our monster spawn controller then, we have our get spawn list. So in our monster spawn logic, we have our get spawn list, and we've passed in the current wave index, which is 1, and we're going to be retrieving that spawn data, which is going to be of type wave data. So that's going to contain the wave index, the spawn monster, and the spawn monster count. So once we have that, we're going to be first checking if the spawn data does not exist, meaning we've reached the end of the spawn list and we've completed the game, in which case we're going to show the result screen. Otherwise, we're going to set up our max remaining monster count to the monster spawn count. We're going to set the maximum spawn count to the monster spawn count. And we're going to set the monster ID to the spawn monster from our spawn data. Then we're going to be setting up our spawn list to be populated based on the entity count of our monster list. So we have the number of monsters to spawn, and this is going to be relevant kind of to our pool. So we're going to get into this a little bit more detail in the next section, but just understand that first we're going to be populating our pool if the pool has not been populated. Otherwise, we're going to be spawning in the monsters based on the number of enemies that are available to spawn from our pool. Then we're going to be spawning in whatever we couldn't spawn that were already available from our pool. So whatever is not in our pool, we're going to be spawning in. So all that to say, we are crafting the enemies. We're going to be retrieving all the enemies that we need to spawn and activate. Then we're going to be calling playMonster on a timer that's going to be repeating every standby time number of seconds. So we have 5 seconds as our standby time. So this is going to be the delay between waves. Then we're going to be calling playMonster based on a repeating timer that is going to be repeating every second. And we have a start delay time as the standby time. So before we start repeating, we're going to first wait 5 seconds, which is the current standby time. And we're going to play each monster. So in our playMonster, we have the loop through all of our spawn list, and we're going to essentially activate this monster and enable and set the monster up so that it can begin looping into our grid. If we have reached the maximum number of enemies that we can spawn, then we're going to clear the timer out. We're going to set the current spawn to 0, and we're going to be doing one of two things. Either we have defeated all of the enemies, in which case we're going to increment the current wave and initialize it. Otherwise, we have still enemies remaining to defeat, in which case we're going to pause the spawning and we're going to update our game logic to pause our wave. Our spawn monster is going to be creating the monster and spawning in the model based on the model ID from our monster data. And we're going to be initializing that monster based on the monster data, spawning them at the corresponding position, and we're going to add that model to the monster list. Next up, we have our update remaining monster count. This is going to be incrementing our remaining monster counter whenever a monster spawns or dies in our map. if the current wave has been paused and a monster had died or spawned, we're going to double check if the remaining monster count is 0, and then we're going to set the pause spawn to false. We're going to increment the wave index because we have no longer any enemies left, and we're going to be disabling the current timer, and we're going to init the wave so that we can start the new wave. Next up, we have our change result UI, which is going to be deactivating all of our monsters when the game has been finished. Finally, we have our call restart, which is going to be reinitializing our data for our waves so that we can restart the game. And that's it. Our game is really taking shape now that the waves of monsters are spawning dynamically based on our wave data. But before we let this game run forever, we have a major technical hurdle to address. Constantly creating and destroying entities will crash our game's performance. In the next section, creating an object pool, we'll learn about a crucial optimization technique to keep our game running smoothly no matter how long the player leaves it open. Let's talk about performance in this creating an object pool section. As our waves get bigger and bigger, destroying and recreating monster entities will destroy our CPU and our RAM. So in this section, we'll explain the concept of object pooling and show you how to pre-spawn a batch of monsters at the start of the game. We'll then use those entities by recycling them and turning them on and off, keeping our game running flawlessly, despite the number of entities. So what is object pooling? Well, to understand that, let's open up our scripts and let's take a look at our monster spawn controller. So if we open up our monster spawn controller, we have our spawn monster method. And if you look, we have our spawn by model ID, which will create a new entity into our scene. The more we do this, the more RAM we're utilizing. As we spawn these monsters in, eventually we're going to need to destroy these monsters. So they might die as they lose health. So they're gonna continuously spawn and destroy and spawn and destroy. So in and of itself, it's not an issue, but as they are created and destroyed, that puts an unnecessary load on what's called the garbage collector, which will try to clean up all of the memory, and that adds extra load, which will start to slow our game down. So instead of constantly creating and destroying entities, what we'll do instead is we're gonna use what's called an object pool. And this is an optimization method to pre-spawn entities at the beginning of the game and only spawn new entities as necessary by reusing the entities that we've already spawned and recycling those in. So these monster models are going to be reused over and over again. And if we go and take a look at our model and we open up our monster, we have two different monsters here. We're not going to constantly spawn in new orange mushrooms or stone golems every single time. We will instead only spawn a certain number of them and keep recycling those same entities. So every time they are enabled or disabled, they're going to be reset with different types of data. So let's take a look at how this object pooling is working. There's different ways to implement object pooling in different projects, but let's see how we're doing it here. So in our init method, we have our spawn entity count, and this is coming from our property that we have predefined up here to spawn 50 entities in. So if our current spawn list, which is our monster list, is empty, meaning that in our spawn monster, you'll see that when we spawn the monster in, we're adding the model entity to the monster list based on that monster ID. So if our monster list is completely empty, then what we're going to do is based on the spawn entity count, we're going to spawn in a number of monsters. So if our spawn list is completely empty, so for this monster list, by that monster ID key, if this table is completely empty, meaning that we have no pool yet, then based on the maximum spawn entity count, we're going to pre-spawn all of the monsters that are necessary for this current wave. However, if we already have a pool, then first we're going to check how many monsters are in our spawn list, and if they're not enabled, then those monsters are available to spawn in our pool. What determines the availability of the monster in our pool is its activation status. So if the monster is deemed available in the pool to spawn, then that monster is set to false. So for example, if you open up our monster component and go into our monster controller, we have our set enable state. So that is going to enable our monster. If our monster is dead, meaning that we have less than or equal to 0 HP, then we're going to play our animation key, and at the end of our animation, we're going to set the activation status to false. So that way, instead of completely destroying the entity, we are instead activating or deactivating it so that when we call init wave, we can check how many entities are disabled, meaning that they're ready to spawn, and how many are not. So based on that can spawn count, we're going to then start spawning in monsters as necessary. So in this way, we are constantly managing a pool of our monsters, and that pool is managed by our monster list. So depending on the monster ID, we have a separate pool for each, and in spawn monster, we are adding to that pool. Then on init wave, we're going to first check if we have a pool or not and initialize. Otherwise, we're going to spawn in monsters as necessary, then begin the wave as normal. Something to keep in mind though is that object pooling is a trade-off. Pre-spawning, let's say 10,000 entities will of course cripple our RAM usage. So you as a developer need to find the proper balance of the spawn entity count, which is going to be the maximum number of entities that can exist in our world that fits the wave sizes without overloading our memory. So that covers object pooling. By pre-spawning and reusing our entities, we've secured our game against performance drops and memory leaks. With the combat loop fully optimized, we need to let the player actually play. So up next, implementing the summon system, we introduce the in-game currency, a hookup summon button UI, and tie all of that into the character gacha logic we built earlier. Welcome to implementing the summon system. So now it's time to give the player control. In this section, we'll cover creating our game logic to manage summon tokens and wave timers. We'll also build our first UI element, the summon button, and hook it up to a localization dataset so it translates automatically. Finally, we'll link this button to our currency and gacha system. So the core of our wave spawning logic is going to be contained within our game logic script. So opening up our logic folder, let's take a look at our game logic. We'll double click to open this up. And we have a couple of properties here. We have the summon token, which is going to be just a counter for how many summon tokens we have. We have our need timer, which is going to keep track of whether or not this wave needs a timer. We have our maximum left time, which is going to be the maximum amount of time left in our wave. We have our time left delta, which is going to be the current tracker for our time. So let's begin our tour of the logic with onBeginPlay. So in onBeginPlay, first we're going to call offline reward. And essentially what this is going to do is it's going to calculate the amount of time that we were offline and reward us with tokens based on the amount of time that we were offline. After that, we're going to call data storage logic and call request load best wave, which is going to be loading our high score. And we're going to get into that in a future section, but for now, just know that we are going to be loading our best wave. So in call offline reward, we're still in the client here, and we're going to delegate this method where we calculate the offline rewards to the server. That way we make sure that the clients aren't the ones that are calculating the offline reward. We make sure that the server are the ones that do it. So in our server, we have request offline reward, and we're going to pass in our user ID, and we're going to call time reward logic load last login time. And if we hop into this method here, we have our load last login time method. And we are passing in the user ID that we want to calculate the last login time for. We're going to retrieve the storage key, which is going to be last login time. And we're going to retrieve our key and value for our login time, which is going to be the amount of time in seconds that we were last online. And we're going to call calculate time reward based on that last time. So in here, we're going to get the difference between our last login time and our current time, which is just going to be the OS time, which is again, returning an integer. And based on that time difference, we're going to calculate the current time difference divided by 10. So what that means is that every 10 seconds, we're going to be returning one summon token. So we have a maximum return value of 10. So if you were away for 2 years, the maximum you'll get is still 10. So we're just capping that. So once we return that value, we are setting that to the offline reward. Then we're going to save the current time so that we update our last login time. In our onSync property, we're going to send a message back down to the client notifying that our offline reward property has changed. So that's what our onSync property is doing. So whenever something from the server side that is marked as sync is changed, then it notifies the client that that has changed and can perform some sort of action or behavior. So here we're going to call game logic update summon token, and in our game logic, we are going to be setting our summon token to our current summon token plus the value that we want to add. Then we're just going to let our UI know that our summon token has changed and display the current updated summon tokens. Okay, moving on, we have our need timer method, which is going to be setting our need timer value to true so that we start tracking our timer for this wave. We're going to set our time left delta to the maximum left time, so which is going to be 10 seconds. And in our on update, if we have our need timer active, which was again set by our need timer method, then we're going to check if our time left delta is less than or equal to 0. If it is, then we have run out of time for this wave, and we're going to update our timer with the time left delta. We're going to set our time left delta to 0, then we're going to update our timer with our time left delta, and we're going to call need result, which is going to show the result panel and update it with things like our best wave and our current wave, and update the UI with the result values. Otherwise, if we still have time left, then we're going to decrement our time left delta by our delta of update. And then we're going to check again for our time left delta being less than or equal to 0. If it is, then we're going to set our time left delta to 0, and we're going to make sure to update our timer with that time left delta. Finally, we have our restart game. And this is just going to delegate all of the respawn behaviors to the relevant components. So for example, our monster spawn controller, we're going to call restart on our monster spawn controller. And our character slot pose group, we're going to clear our character list. We're going to update our summon token. If our summon token is 0, then we're going to make sure that we have at least 1, and we're going to disable the timer. Disabling the timer is simply just going to set the need timer to false and update our UI to disable the timer. So now that we understand the baseline logic behind our wave and how all of the general behavior works, let's take a look at our UI. So to spawn a character in, we have our in-game UI. So let's change the group so that we're looking at our in-game UI. And we have this summon button here. So this summon button right here, this is just going to be a sprite GUI render component with a button component attached to it. Notice that in our summon button, we have a child with a text component in it. And this text component doesn't really look like the summon text. It has kind of like what looks like a key, and that's because it is a key. We have this is localization key box checked, and what this does is this allows this to act as a key for our localization table. So if we open up our data table here, we can see that we have a table called string data, and this is going to be our localization table. So let's remember UI underscore summon. Let's double click to open up string data, and we can see that we have our UI underscore summon here, and we have translations for Korean and English. And this is going to allow us to automatically retrieve the correct character string based on the selected language of our client. So it'll use this text as a key and retrieve the correct string. So we're going to manipulate our button component so that when we click this button component, we actually trigger the spawn logic. So if we look over at our in-game UI, we can see that we have an in-game UI controller. If we double click to open this up, we can see that at the bottom we have our handle button click event that is connected to our summon button. So what this is going to do is it's going to listen in on this entity for this button click event. Every time the user clicks on this button, it's going to send this event to this entity. And this component here, in-game UI controller, is going to be listening in on that entity for this event. So whenever this entity raises this event, we're going to listen in on it and perform this behavior. So the behavior we're going to perform on button click is going to be our character gacha logic's request spawn character. If we take a look inside a request spawn character, we're going to first double check if we have enough tokens, and then we're going to spawn our character to a slot. Otherwise, we're going to let the user know that we need more space. If we don't have enough tokens, then we're going to show that we need a token to spawn our character in. So there is that summon token variable coming into play from our game logic. So outside of the offline rewards, how do we actually gain currency and how do we gain more summon tokens? Well, if you look at our component script and we go into our monster controller, we have our get damage method. Inside of our get damage method, we're going to check our current HP. If it hits 0, then we're going to update our summon token and add 1 to that summon token. So that's how we're gaining summon tokens. For the monsters, whenever they die, we are going to reward the user with 1 summon token every time. Awesome, so players can now earn tokens by defeating monsters and spend those tokens to summon heroes via our localized UI. The core gameplay loop is now fully playable, but what happens when the player closes the game? In our next section, implementing save and load will ensure all their hard-earned progress is safely stored on the server so they never lose their best wave record. So in this section, implementing save and load will tackle one of the most important aspects of any game, player progression. Here we'll use data storage logic and data storage service to save the player's best wave to the server. We'll also discuss the relationship between the client and server variables and how to use sync properties to automatically update the client's UI when data loads. So the core of our data storage model is going to be contained within our logic script, our data storage logic file. So if you double click to open this up, we have a couple properties here. We have our server best wave, which is going to be the best wave value stored on our server. We have our client best wave, which is going to be the best wave value for our client. And we have our storage key, which is going to be the key that we use to save and load our best wave information. Let's start with saving. So in our save best wave method, we're going to pass in the user ID and the best wave value. We're going to set our server's best wave value to the best wave. We're going to retrieve our data storage based on the user ID. Then we're going to save the best wave based on our storage key, which is currently set to best wave, to the server's best wave value set to a string. Then as long as we don't have an error, we're going to successfully save. Otherwise, we're going to print out the error code. And for loading our best wave, we're going to retrieve again our user data storage based on the user ID. We're going to get the storage key based on the storage key property up here, currently set to best wave. And we're going to retrieve our key and our value. So as long as our error code is 0, meaning success, we're going to convert our string value to a number. Remember when we saved it as a string. We're going to return that as a number value again. If we fail to do that, then we're just going to set it to 0, and that will be the loading. So our server now knows the best wave value, but our client needs to be communicated that value so that when we retrieve this value from the client side, we have the value available. The client can't directly access server properties, so that's why we have a client version of our server best wave. So on our onSync property, we have our server best wave. We're going to check for this property when it's updated on the server. We're going to check it on the client side, and we're going to set our client best wave value to this value. And this just ensures that our server property is the one that is saved, and we are not tracking based on the client's value. Now you might be wondering why we have a request load and a request save both on the server side when we already have server side saving and loading methods. And if we open this up, we can see that all we're doing is we're just delegating this to the server only methods for loading and our saving. So if we have a method in our server execution space that can still be accessed from the client, meaning that there's still a security risk in that our client can still access and call these methods. Whereas if it's server only, the client cannot directly access these two methods. So this kind of acts as a bridge between our server and the server only methods that cannot be directly called by the client. And ideally what we might have here is maybe some sort of security measure to ensure that only the correct people can access the server best wave and the server load best wave. So just to make sure that the user ID matches the requester and is not attempted to be loaded by someone that isn't the owner of this user ID. Another thing to mention is that Currently, the server blindly trusts the value that is coming in from the client side and saves that as the best value. But ideally, to prevent hacking and additional security measure, we should ensure that this best wave is handled and calculated only on the server side. So even the best wave calculation should ideally be handled from the server side. But because this example is purely client driven, we're just going to keep this as is. In our MapleStory Worlds documentation, we have a detailed guide on the client and the server, as well as a section on security and optimization that will make sure that you understand how to secure your server-side code from hackers. So please refer to this documentation for more info on that. So now we have a reliable way to save and load the player's best wave using server synced properties. This guarantees that progress is never lost. Speaking of progress, idle games thrive on rewarding players for coming back. So in the next section, we'll take a deeper dive into implementing offline rewards, and we'll build a system to calculate how long the player was gone and reward them with summon tokens upon their return. Welcome to implementing offline rewards. This feature is the heartbeat of player retention in idle games. In this section, we're going to build our time reward logic to save the player's last login time. We'll then calculate the difference upon their return and reward them with the currency based on how long they were offline. We'll also cover some best practices for taking the system commercial. So why do we implement offline rewards? Well, especially in idle games, offline rewards are kind of a psychological tool to increase player retention and daily return rates. If the players know that when they return to the game, they're going to get a lot of reward, then that incentivizes them to keep returning to your game over and over and over again. This, in a way, even gamifies the time that they were even away from the game. So this is a great strategic tool to make sure that your players keep coming back. Okay, so the core of our logic is contained within our time reward logic. We have a couple properties here. We have our storage key with our last login time. So this is going to be what we use to retrieve our login time from our data storage service. We also have our offline reward value, which is going to be the actual value for our offline reward. Then we finally have a kind of Boolean flag to make sure that we don't duplicate the login time and we're not calling this multiple times. So once we've claimed our offline rewards, we cannot claim it again. So in our game logic, in onBeginPlay, we have a method for call offline reward. And if you remember, we have a server-side request for load last login time, and we're passing in the user's ID. So in here, we are calling load last login time, and we're going to retrieve the user data storage based on the user's ID. Then we're going to, using our storage key, which is last login time, we're going to retrieve our key and value pair for our last login. So this will be the time in seconds that the player was away. So when we retrieve our last login time, we're going to retrieve it as a number value. This value is going to be stored as a string property. So from string, we're going to return it back to a number type, and then we're going to calculate our offline time reward. So in our calculate time reward, we're going to set our flag offline reward complete to true, just so that this cannot be claimed twice. Then we're going to calculate our current time, which is just going to be the OS time, which is again an integer in seconds representing the current time. We're going to calculate the difference between our current time and the last login time value that we're loading in. Then we're going to check if that time difference is less than or equal to 1, in which case we're just going to return 1. So that means that no matter how much time you are away, even if it's very, very, very short, you will at least get 1 token back. Otherwise, we're going to calculate the time difference divided by 10. So that essentially means that every 10 seconds, you're going to get 1 summon token. We're also going to cap this value though, so that our return value is never greater than or equal to 10. So if you're away for months and months and months, the maximum amount you will still get is always going to be 10. And then we're going to return that value to our offline reward, and we're going to save that current time. When we save it, we're going to retrieve our user data storage again based on the user ID, and we're going to save our current time as a string to that storage key, again, same storage key. As long as it's successful, we're going to log out that we have successfully saved our current time. Otherwise, we're going to log out the error code. So keep in mind, when we save it as a string, when we load it, we are converting it back into a number. Finally, our offline reward was set in our load last login time method. So our client now needs to be notified that our offline reward has changed. So we're going to utilize our onSync property again. And again, this is going to just check whenever a value on the server is marked as a sync property, it is going to synchronize that value down to the client and let the client know that this value has changed. So whenever our offline reward has changed, we're going to call update summon token in our game logic so that we update our summon token with the corresponding value. So we're going to increase our summon token with the value. One quick warning that I'll mention is that when calculating time on the client side is vulnerable to device time manipulation, meaning players manually advancing the phone clocks. Commercial games generally implement secure time validation as well as a dedicated claim reward pop-up UI. Couple things that you might want to double check in your code and might want to expand on the existing code further is to double check the player's region, make sure that the player's region hasn't changed, maybe the time zone has changed, something like that. So take that into consideration when you're calculating the time. Another thing is the current implementation does not use data sets. So consider using data sets to allow expansion of even more types of rewards for better organization of data. At the moment, we only have tokens, but maybe you want to add more things to the pool of rewards that the player can get for the offline rewards. Finally, there is currently no visual way to claim the reward. Everything is just kind of happening behind the scenes and there's just a log that happens. But ideally, there should be a visual implementation of claiming your reward. So do recommend implementing a claim the reward button visually so the player knows that they have claimed their reward. So that's it. Our offline reward system is now calculating our time away and injecting tokens directly into the player's wallet when they return. It's a fantastic way to build a habit-forming game loop. To tie this whole project together, we need to make sure that the player can actually see all the information clearly. So in our final section, configuring the UI, we'll polish our game over screens, our HUD, and introduce a crucial optimization pattern for UI management. Welcome to the end of our journey in our tutorial, configuring the UI. A great idle game requires clear and satisfying visual feedback. So in this section, we'll take a look at how UI groups handle layering, building a responsive game over screen, and inject dynamic text. Most importantly, we'll introduce a bridge pattern via the UI manage script, a major optimization trick to keep your game running smoothly without messy and tangled code. Let's start off with our result UI. So we'll open up our UI tab here, and let's change our group to the result UI. So here is the result screen that we saw earlier. Notice that our result UI has kind of a semi-transparent black background. This is kind of a barrier that makes sure that anything behind this UI cannot be clicked. So if we open up our UI here, we can see that we have a non-click BG, and this is just going to expand the width of our entire screen and expand actually even a little further. The reason for this is because certain devices, especially on mobile, have mobile save screens. So this anchor point at 0000 for a full stretch is based on that safe zone. So for certain devices that have a safe zone that is smaller than the actual visible range of the screen, this would still be kind of not fully covering the entire screen. So we're going to expand -300 on all sides to make sure that we cover all devices and all safe zones. We've also got our result text, which is just going to be the title. We have our goal frame, which contains the goal text. We have our restart button, which is going to allow us to restart our game upon clicking. And again, remember that we do have this as a key for our localization key. Whenever we try to load this text, we're loading them based on the localized version of that text. One last thing to keep in mind is that in our goal text, we have this kind of strange format here where we have these curly braces and a number in the middle of them. What we're going to do here is we're going to dynamically inject text into wherever it says here. So we're going to localize this text, but we're going to dynamically inject text into where the curly braces are. Okay, so with that, let's take a look at the controller for this UI. So let's double click to open up Result UI Controller. And first up, we have our goal text, where in onBegin play, we have init goal text that will just initialize and find that goal text from our path. So if you just right click, we copy our entity path, that will be the same as this value right here. And then, as long as we can find the entity, then we're just going to set our gold text to the entity's text GUI renderer component. So we're going to grab the text GUI renderer component of our gold text. So that's just some initialization steps. Next up, we have our update result text, where we are setting the gold text value to the localization service get text format UI underscore result wave. So this is going to be the key that we're going to set this gold text to. So remember that we had this as our value. Well, we're going to manually pass in the key, which is going to be UI underscore result wave. So let's open up our localization table and take a look. We have UI underscore result wave here. And that kind of has the same format that we saw in our gold text. So we have a curly braces 0 and a curly braces 1. What's going to happen is we're going to replace curly brace 0 with our achievement gold count that we're passing in. We're going to replace our curly braces 1 with our best gold count. So we're basically just injecting text into where the curly braces are through our localization service. Same thing for our English. We have a English localized version of this, and it's just going to do the same thing, inject into 0 and inject into 1. We have our show and hide method, which is just going to modify the enable status of our entity. And then finally, we have our button click event hooked up to our restart button. So our restart button, when clicked, it's going to hide our current result UI, and it's going to call restart game on game logic. So that's just going to restart a game so that we can play it again. So that is our result UI. Next up, let's take a look at our in-game UI. So let's switch to our in-game UI, and here's all of our UI here. Let's open this up. So we've already taken a look at our summon button. Our summon button is going to summon in our units when we click it. We also have our monster count up here, so that's going to be the number of monsters in our wave. We also have our wave count. This is going to be, again, our dynamically localized version. We can see the familiar pattern of our curly braces here. We have our left time, which is, again, that same pattern where we inject values into our localized strings. Then finally, we have our summon token, which is going to be the number of tokens that we have available in our wave. So let's take a look at the controller for this. So we're going to double click to open up our in-game UI controller. And we have a couple properties up here, and we're going to initialize all of them inside of our onBeginPlay. So we have our monster count text, which is going to be this value here. We have our wave count, our summon token text, we have our timer entity, and we have our timer text. So our init monster count text is going to set our monster count text value to the entity at this path. So it's going to be monster count, and we're going to grab this entity here, and we're going to grab the text GUI render component of that count text. For our init wave count text, it's going to be very similar. We're initializing the UI for this. We're going to grab our text GUI render component from the wave count. So we're grabbing this entity right there. We have our init timer, which is going to set up two things. We're going to find our timer entity at this left time. So we're going to grab this entity here. And then we're going to grab the text value for the timer text. So first we're going to grab the parent for the left time. So for waves that have a timer, we're going to need this timer. For waves that don't have a timer, we're going to need to disable this. So that's why we're grabbing both. One to be able to set the activation status, and one to be able to set the actual time left. And then finally, we have our init summon token. Again, we're going to be grabbing the icon image. So summon token, icon image, and then the summon token text. So we're going to grab this and grab the text GUI renderer component from this entity. So let's run through the update methods for our in-game UI controller. We have count left monster, which is going to set the monster count to the UI remaining monster count. So again, let's take a look at the localized string for UI remaining monster count. We have 0, and this is going to be the localized text. We don't really have any localized difference between Korean and English, but if we wanted to add localized versions of this string, we can in the future. But for now, we just have 0, 0 and 0, 1. We also have our update wave count. This is going to follow that similar pattern of localization, get text format, and we're gonna grab the UI wave count. So that will be this value here. So we have wave. Both are the same in Korean and English, but if we wanted to actually localize it, we could. So we're gonna inject our wave count into this curly braces 0 here. So that's what we're passing in, and that's what we're setting in our formatted text. Next, we have our update summon token UI, and very similar, we're just going to be setting our summon token's text to the floored value of our summon token value, and we're going to set that as a string to the summon token text. Okay, so that is our in-game UI controller. So we've gone over both controllers for our in-game UI as well as our result UI. So those are the two core UIs in our game. But how do we actually communicate to these controllers? We saw in a lot of our code that we are referencing our UI manage logic. But what is the purpose of UI manage logic if all of the behavior for our components are contained in the components themselves right here? Well, our UI manage logic is going to be what's called a bridge pattern, where because we have a globally accessible component, we have a globally accessible logic script here, we delegate the access to our UI components to our UI manage logic. So let's say every monster needed to update the UI. If every single monster were to have a reference to our UI component, then that could cause severe lag and it could start eating up a lot of memory bandwidth. So instead of that, we're just going to utilize our bridge and not actually need a reference and store our component reference in memory. So for example, methods like our show result UI is going to call our result UI controller's update result text that we saw. So our UI manage logic is going to hold the component reference in memory, and it's just going to delegate behaviors to the corresponding controllers. So we're going to call update result text and our show methods. Other things like our update monster count, we're just going to delegate our monster count updating. We're going to pass in the current and our max into the in-game UI controller, and we're going to pass that into the count left monster method that we saw earlier to update the UI for that. And this is going to be a very similar pattern for all of the other ones as well. So like summon, update summon token, we're going to pass in the token value and delegate the behavior to the corresponding controller. So in this way, our manager handles the finding of the UI and keeps our game highly optimized and the code clean. And that brings us to the end of this tutorial. We've covered so much here, like how to design responsive UI screens, format dynamic text, and drastically optimize our code using a central UI manager. We've gone from a blink map to a fully optimized localized idle game with offline progression, object pooling, and a satisfying auto-battler loop. Thank you so much for joining me on this deep dive into our idle sample world, and I hope you can take this even further and build your own ideas into this world. Happy developing!